Welcome back 3U and 4C chemistry students. So today we're going to do a little bit of review with mole calculations, and then we're going to move into some slightly more complicated examples. So first of all, you'll notice I have something here called a master formula. It's really not a formula, it's more of, just a way to organize things in your mind. So we've looked at mass in grams. We've looked at this neat thing called moles, which is a very convenient way of talking about things in chemistry. And then we can have individual pieces. So those are the three entities that you have been doing some conversions between. You've been able to calculate if you're given a mass, you've been able to figure out how many moles. And how you did that was you used the conversion factor of molar mass, where grams had to be on the bottom because you would be starting with mass, which would be in grams. That would bring you to moles. Similarly, you've done some questions where instead you went the other way. I gave you the moles and you figured out the mass. You use the exact same conversion factor. It's still molar mass, but notice how it's written upside down now, so to speak, because since you're beginning with moles and heading in the left direction, you would want moles on the bottom. And then we've also been able to calculate between moles and actual pieces or particles. And with chemistry, that's probably molecules or atoms, but it could also be ions, formula units, basically little tiny things. So once again, we had a second conversion factor called Avogadro's constant, and you could use it if you're moving from moles to particles. You would use this version because you would want moles on the bottom to cancel with your moles. If you're going the other way, where you had, some atoms or some molecules, some kind of particle, and I asked you for moles, you'd use this version, which would be upside down. So we're going to keep that in front of us because today we're going to look at calculations that require more than one step. So clearly there's our two steps, but we're literally going to have to do it in two steps. All right, so first example, I want to know how many pieces, or in this case atoms, of sodium I have if I have a 5-gram sample. So you can see that I'm starting way over here at mass with 5 grams, and I need to get over here to atoms, or the individual pieces. So every time there's like the big dark arrow, that's telling you you have to do a math operation with a conversion factor. So we're going to start like we always do. We're going to start with what you're given. So the 5-gram sample of sodium, and no matter what, you have to multiply it with something that has grams on the bottom. And if you look at all of our conversion factors, there's only one of them that works. It's this form of molar mass. So we're going to have mass on the bottom, and we're going to have 1 mole of sodium on top. Now, we're going to have to look that up on the periodic table, and it is 22.99 grams is the molar mass of sodium. So then if we do that on the calculator, we're going to get something like that. I'm going to jot down 3 numbers. I can tell from my question, my final answer is going to have 2 significant digits. So by putting down 3 numbers, I'm kind of being safe. Okay. Now that is not my final answer, because at this point I'm at moles and I wanted atoms, sorry. So I need something with moles on the bottom and hopefully atoms on top. And that is Avogadro's constant. 6.02 times 10 to the 23 particles, in this case atoms. Squeeze that in here. Is always 1 mole. Kind of made this a bit messy, but okay, so I tend to do this. When we got our first answer here, I don't even clear the calculator because you're going to get the most accurate result if you don't. So with your calculator uncleared, you'll have 0.217, probably a whole bunch more numbers. Now multiply by 6.02. We can use the cheater method and just attach the times 10 to the 23 afterwards. So I believe you're going to get like 1.31, and then you're going to add your 10 to the 23. And at this point, our unit that is left, grams canceled here, we had moles left, which was here. Now moles got canceled. What do we have left? Atoms. And of course, you should always write what it is we're talking about. So atoms of sodium. Now, significant digits. 5 grams had 2, so really the best answer is going to be 1.3 times 10 to the 23 atoms of sodium. Expressed to 2 sig digs. Okay. A question like that would be worth 3 marks because you've done 2 steps of math, and then you always get 1 mark for getting the correct final answer. Okay, so in this one, I might just scroll back here so we can take a look, but we're asked for a mass from a number of particles. So I have a certain number of water molecules, and I want to know what the mass of that is. So we're starting over here with some molecules, and we're working our way backwards. So we're going to use the exact same conversion factors, molar mass and Avogadro's constant, but they're both going to be upside down compared to what they were in our first question. Now, before we start, anytime a question has mass, either asked for or given, if you see mass in the question, you're going to need the molar mass. So to avoid you having to clear your calculator, just do it first. So molar mass of H2O is going to be needed. So we're going to have 2 hydrogens plus oxygen, which is going to be 18.02 grams per mole, because we're going to need it. All right, so 1.67 times 10 to the 25 molecules of water. And I'm going to start working my way across that master formula. Molecules has to go on the bottom. And my conversion factor is going to be molar mass. So 1 mole is going to be 6.02 times 10 to the 23 molecules. And I think I'll just put my answer down here, just because it's kind of be a little bit squishy over there. So we're going to use the cheater method. So just take 1.67 and divide by 6.02, and you'll get something like this. And I'm going to jot down 4 numbers because in the end I'm going to want 3. And then remember, when you divide, you actually subtract the exponents. So 10 to the 25 subtract 10 to the 23 is going to be 10 to the 2 that is left. Okay, so at this point now we have moles of water. And you could clean it up now, but it's fine because remember, it's actually almost better if you just don't even clear your calculator. So we can leave it looking funny at the moment. Now, our final step is we're trying to get to mass. Molecules are now gone. We're at moles. We're going to have mole on the bottom, 1 mole, and in this case of water, we already worked it out, is 18.02 grams. So now moles is going to cancel, and our final answer is going to be grams. So again, I'm just going to take this number and times the 18.02, and then just not forget to tag on this 10 to the 2. So I believe when I do that, I get 4.998. Can't forget about the 10 to the 2. This is now grams of water. And I want to clean this up quite a bit because I do not have the right significant digits. I'm allowed 3. So I'm going to keep the 499 and look at the 8. So the 8 turns that into a 10, that turns that into a 10, that turns that into a 5. So I end up with 5.00 times 10 to the 2 grams of water. That's in scientific notation. Honestly, that is 500. And that is fine too, because that also has 3 significant digits. So a bottle of water that you probably drink from more than likely holds 500 milliliters or 500 grams. And now you know when you drink it, you have drank 1.67 times 10 to the 25 molecules of water. Okay, that is it for today. Thanks for listening.